Today in physics, we'll be talking about an object in two fluids. So here's a problem. We have a 2 centimeter thick bar of soap. So here is our 2 centimeter thick bar of soap, and it's floating on a water surface, such that 1.5 centimeter of the bar is underwater. So this is our water level, and we know that this total is 2.0 centimeters. And the part that is underwater is 1.5 centimeters. And this is our soap. Now, bath oil of specific gravity is 0.6. So, which is to say, specific gravity of the oil is equal to 0.6. Now, specific gravity just means the ratio of the density of oil, in this case bath oil, to the density of water. So equivalent, we can also write the density of oil is equal to 0.60 times the density of water. So we're told that, okay, we start off with 1.5 centimeters of the bar is underwater, but it's still floating. Now we're adding bath oil, and it floats on top of the water. So if this is our water level, we're going to have oil on top of it. So this is our oil level. And then it asks, what is the depth of the oil layer? So what is this? H. Depth of the oil layer when the top of the soap is just level with the upper surface of the oil. So we have our soap here, and it's just level with the upper surface of the oil. So this is our soap. So here we have two scenarios. The first scenario, we already know everything that's happening. But for the second scenario, we're asked to find this height h. So let's start off with the first scenario. So scenario 1. Since we're given that it's floating, we know that it's not going anywhere, which is to say that it's in equilibrium. So let's draw a force diagram of what's happening with our bar of soap in case 1. So we have the weight of our bar of soap, which is just the mass of the soap, we'll call this mass m, times g. Now we want to express m in terms of volume and density because we don't actually know the mass of our bar of soap. So we know that this is equal to the volume times the density of the soap times g. Okay, we also have another force. We have the force of water, the buoyancy force that is also acting upon this object. So it's acting in the opposite direction of gravity. So this is our buoyancy force. Buoyancy force B of water, or H2O. So our buoyancy force is equal to the volume that has been displaced. So this here is our total volume when we're dealing with mg. But when we're talking about buoyancy force, we're looking at how much volume has the bar displaced of water. So in this case, if we call this area A, so this surface area is A, then in order to get volume, we simply have the volume of how much water has been displaced. We have this is 1.5 centimeters, so the depth is 1.5, but the A remains the same. So to get volume, we have 1.5 centimeters times A times the density of water, or the density of H2O, times G. Since it's floating, we know that it is in equilibrium, so these two oppositely directed forces their magnitudes must be equivalent to each other. So we have 1.5 times A times the density of water times G is equal to the total volume times the density of the soap times G, or equivalent, we can write our total volume as 2.0 because that is the depth of the actual soap bar times our surface area A times the soap, the density of soap times G. And we'll copy this over from before. Now we have a few things in common. We have A on both sides and G on both sides, so we can cancel to get 1.5 times the density of water is equal to 2.0 times the density of soap. So we can find that we find a ratio between the density of water and density of soap, or also known as the specific gravity of soap. So we can rewrite it in terms of what the density of soap is. So we find it's 1.5 over 2.0 times the density of water. Okay, now let's look at the second situation. We're asked to find the depth of the oil layer when the top of the soap bar is exactly level with the top of the surface of the oil. So in this case, let's draw a force diagram again. We still have the gravity acting upon the soap. So we have the total volume, which is equal to 2.0 times A, where A is the surface area of the top part of our soap bar, times G, and also times the density of the soap. But now we also have two buoyancy forces. We have the buoyancy force of water. So this is the buoyancy force of water, and that is equal to not 1.5 times A, because now we don't know how much of the bar is in the water. We have 2.0 minus H times A times G times the density of water. So this is all equal to the buoyancy force of water right here. We also have the buoyancy force of the oil that the oil exerts upon the soap. In this case, it's H times A times G times the density of the oil. So because our bar is floating, then it is in equilibrium, which is to say the two upward buoyancy forces must be equivalent to the weight of the bar. So we have 2.0 times A times G times the density of the soap must be equivalent to the buoyancy force of the water plus the buoyancy force of the oil, which both are exerted upon the soap bar. So if we plug in the buoyancy forces, we find that the buoyancy force of water is just 2.0 minus H times A times G times the density of water plus AG times the density of the oil. Now, once again, we have AG on both sides, so we can cancel those out, and we have 2.0 times the density of soap, which we found is actually related to water. So we have 2.0 times the density of soap. The density of soap is equal to 1.5 over 2.0, the density of H2O, which is equal to 1.5 times the density of H2O. And we know that this is equal to 2.0 minus H times the density of H2O plus H times the density of oil, which is just 0.6 times the density of water. So now all we have to do is solve for H. We find we also have the density of water on both sides, so we can cancel to get 1.5 is equal to 2.0 minus H plus 0.6 H. So now in this case, we can have our H's on the same side and move our numericals to the other side. So if we move both H's here, then we get 0.4 H is equivalent to 2.0 minus 1.5 is equal to 0.5. Thus, our H is equal to 0.5 divided by 0.4 centimeters, which we can also write as 1.3 centimeters. So we find that the depth of the oil layer is 1.3 centimeters.